Now we'll talk about normalization. What is normalization? Let's say for every element in our data set, what we do is we subtract our mean from each element, and then the resulting value we divide it by the standard deviation, and we replace the original value with this value that was obtained by this expression. Okay, so let's say for a given data set 2, 3, 4, 5, I'm just taking 4 values. I can say that as x0, x1, x2, x3. Please calculate x0 dash for me, x1 dash for me, x2 dash, and x3 dash. Everyone just take one of the values and please calculate. Okay, finding the standard deviation will be a very big problem. Okay, okay. So we will. I do not want these values. Just forget it. So they'll be calculating standard deviation, mean, and everything, and finding these values will be a very. So you can try and do that later. So what would happen is, after you have done this, what will happen is that you will notice that now your mean will be 0 and the standard deviation will be 1. After doing these operations, the new values that you get, the new value will be x0 dash, x1 dash, x2 dash, x3 dash. Right? So if you will try to find the mean and standard deviation of this particular data set, what would be observed that the mean is 0 and the standard deviation. And why we do that? Because after doing this particular operation, what would happen is that now your mean will be at the 0 and your standard deviation will be very much standardized around this mean. And what that means is basically, let me take this example. So what normalizing would do is it could make your data scale and translation invariant. So what that means is, let me give you an example. Let's say we apply some scaling to this. In that case, let's say I do plus 2. Then my data set would be 4, 5, 6, and 7. Now what would happen? Here the mean, it will also be shifted by 2. That is very much true. Since each of the xi's has been shifted by 2, the mean will be shifted by 2 as well. And now, since the spread of the data has not changed, on a given axis, the spread is exactly the same. Standard deviation will remain to be same, because while calculating standard deviation, we do xi minus mean x, sorry. So what that means is, doesn't matter that what is this translation value, it could be any plus k. The new values will be invariant to this k. Alright, and that exactly is true for scaling also. You can go ahead and try it with an example later words, but whatever the parameters of translation and scaling are, after normalizing, the impact of translation and scaling on the newly calculated mean and standard deviation neutralizes, because now the mean and standard deviations are well defined. Mean will be 0 and standard deviation will be 1. Okay, and that is why we normalize our data, so that if there are any scale related or translation related variance or like discrepancy within the different elements of a data set, they get removed. Okay, so after normalizing the data, we can use the data while being very much sure that the scale and translation variations, if any, in the data will be neutralized. So now, coming from this concept of normalization, let's say if you get a curve which is perfectly similar to this standard normal curve, where the mean is at 0 and most of the data is divided around this mean in such a way that 68% of the data lie within one standard deviation of the mean. I.e., let's say if your standard deviation is up to here, this area will be, Let me draw it like this. So this area will be 68% of our population in terms of the frequency. Then 95% of data would lie within two standard deviations from the mean. I'm trying to do my best to identify. So now within these limits, we'll have 95% of the data, and then within three standard deviations from the mean, we will have 99% of our data. And if we have any such curve, we say it to be a standard normal curve. And if you want to derive such a curve, there is an equation for that. And this is what you have also derived when you had studied about normal distribution in 11th or 12th class when you studied statistics and distribution. Do you recall that? No. So now what are the outcomes of this making our data scale and translation invariant? Is that if there are two different data sets having different units of measurement, they can now be compared after normalization, or they can be studied on the same scale. Alright, you can also compare them, or you can merge them together and plot them together. So that is the major advantage of normalization. When we'll further go on to study machine learning algorithms, we'll again rediscuss the impact of normalization. Normalization can make major differences into our learning outcomes. Alright, any doubts till now? I will continue to the next section. Do you want 5 minutes break?